So in this video, I'm going to talk about angular velocity and angular momentum. So far we've already gone through a unit where we've talked about stuff moving in circles, right? So when we did our centripetal force and circular motion unit, you had an object that was traveling in some circular path. And when we dealt with these types of problems, we were always talking about the tangential velocity, or the sort of the instantaneous speed at this point, and it was always in meters per second. Now, we also talked about frequency, and so let's say an object is traveling around in a circle, and let's say the frequency is 5 revolutions per second. That means that every second they go around the circle 5 times, right? Now, we can relate this to angular velocity. So angular velocity is just thinking about the velocity of the object or the speed of the object in terms of the change in the angle rather than the actual distance that's being traveled. So instead of having meters per second, we're actually going to have radians per second. So as you go around the circle, we know that going around the circle is 2 pi radians, right? So if I were to convert this to radians per second in order to get my unit into angular velocity, I would just multiply by 2 pi, and I would get that's 10 pi radians. Oops, I forgot my pi. 10 pi, and then the unit would be radians per second. This here is an example of an angular velocity. Now, angular velocity, the variable that we use for angular velocity is the Greek letter omega, but it's a lowercase omega, so it looks like kind of a squirrely W. All right. The other equation I kind of want you to know before we move in and look at the example of conservation of momentum, angular momentum in this case, is how does this actually relate to the actual instantaneous velocity? And the equation for that is that the velocity, if I were to take the angular velocity and multiply it by the radius, that would actually give me how fast I am moving around the circle, or my instantaneous velocity. So angular velocity times the radius of the circle is equal to the actual speed that this object is going, and the same velocities we talked about when we did tangential velocity in our previous unit, right? Now I kind of want to relate this idea to conservation of momentum. So if you were to have a figure skater, and as a figure skater does spin, if they pull their arms into the center, they start to go faster. That is because of the conservation of angular momentum. The equation for the conservation, or for angular momentum, is mass, so this momentum is equal to the mass times the angular velocity times the radius squared. Okay? So let's say that we were to have something, an object, and it's rotating in a circle, right? And let's say it's going in this direction, and we'll just say it's going 5 radians per second, right? So this would be my angular velocity, and it has some distance or some radius of the arm here, and I don't know, I'll just make a number up. Let's just say it's 2 to make it easy. 2 meters, right? If the object were to, say, retract its arm or pull it in here, we could then actually calculate using conservation of angular momentum to figure out how fast it was going, right? Now the mass is going to stay constant, so we know that it's going to actually cancel out. So how I would set up, remember, all of our conservation problems always deal with whatever the momentum is at the beginning must be equal to the momentum after some change in some variable has been made, right? So the angular momentum, like kind of before the retraction, must be equal to the angular momentum after the arm sort of retracts in. Let's say it goes in to a distance of 1 meter, right? So we know intuitively from, thinking about the figure skater idea that this thing must be going a lot faster, right, as you pull the mass in towards the center of the object. So if I were to look at this, we know the mass doesn't change, so the mass cancels. And before, I know that I'm going 5 radians per second, and if I multiply that by, remember our original arm length was 2, so it would be 2 squared, is equal to our angular velocity now times the radius squared, which would just be 1, right? So this ends up being 4, so you get 20 is equal to angular velocity times 1, and it's very easy, I don't have to use a calculator, and I know that the new angular velocity after the arm has been pulled in is equal to 20 radians per second, right? Now, let's look at what this means, right? So if I were to, we know that the radius in this equation is squared. So as the radius gets smaller, we know by some square the velocity is going to have to get bigger because this is a quadratic. Now, just so we can go back and sort of connect this idea of radians per second with velocity, because to me, intuitively, 20 radians per second doesn't really mean anything to me. Like 5 meters per second means something to me. 20 radians per second really doesn't mean a lot in terms of how fast something is actually going. So let's change this and use this equation to change it into a velocity, right? So at first we have 5 radians per second, and we have a distance of 2 meters, right? So if I were to multiply that, your angular velocity times the radius, so it would be 5 times 2, then my instantaneous velocity right here would be 10 meters per second. And then as I pull my arm in, now I'm going 20 radians per second, and my radius is 1 meter, so I just take that and I would say, all right, 20 meters per second. So my actual tangential velocity doubles in this case as the length of the arm is cut in half, while the angular velocity is actually squared. Right? So hopefully this is just a basic introduction to the ideas of angular velocity and angular momentum, and we will do some practice problems involving these concepts.